Now, it is time to talk about, perhaps, the most famous of all hominids, the Neanderthals. We call these hominids Neanderthals because the first bones of these people were found in the Neander Valley in Germany. Valley in German is pronounced Tal, and therefore the H is silent, so it is Neanderthal and not Neanderthals. The first remains of these people, these hominids, were brought to the attention of scientists in 1856. Now think back to Module 2 and remember what was going on in the European science world in 1856. What year did Charles Darwin publish Origin of Species? 1859. So evolution by natural selection, it wasn't a thing yet, and into that static worldview was brought a set of human-like remains. What to make of them? Well, the doctors and anatomists that study these fossils noticed a few oddities. First, that protruding bit of bone over the eye orbits, that's definitely unlike any living person today. They also noticed that one of the humeri was broken, badly healed, and the legs bowed as though the person had suffered from rickets. Could these oddities shed light on the person to whom the bones belonged? One idea was that these were the remains of a Cossack soldier. Cossacks are East Slavic people from Ukraine. They long served as border guards and men for hire to fight in Russian wars. After Napoleon had invaded Russia, the French army was chased back by the Cossacks, and that army had camped right near the cave in the Neander Valley, right where this Neanderthal's bones were found. So maybe this was a deserter from the Cossack army. He would have been pretty unhappy with, the injured elbow, with having suffered from rickets all of his life, so he probably would have frowned a lot, which could have led to the odd, peculiar brow ridges. Well, more bones continued to be found, and it became evident that this was not a one-off skeleton, but there had been people living in Europe who looked quite different from the people who live there today. These people came to be known as the Neanderthals. The suite of characteristics that we associate with Neanderthals appear all together in fossils from Krapina in Croatia 130,000 years ago. The youngest Neanderthal fossils are from 30,000 years ago in the southeastern part of the Iberian Peninsula. This was, in a sense, the last stand for the Neanderthals, 30,000 years ago. So Neanderthals were around as a distinct population for 100,000 years. Now those distinctions eventually became motivation enough for William King in 1864 to name a new species, Homo Neanderthalensis. Now, one of the funny things about his species diagnosis was that he said that these creatures lived in moral darkness, and that was why he wanted to name them a different species. Now, it is most unusual to name a species based on moral characteristics, but there definitely are some clear distinctions between Neanderthals and modern humans. I have a picture here of a colleague of mine, Alban de Flor, a French archaeologist who has actually excavated quite a few Neanderthals in his lifetime. And he's eye to eye, nose to nose, with a statue, a 3D bust of a Neanderthal, created, an artist creation from the shape of the bones underneath. So let's look at them. Let's compare them. They're eye to eye, which helps with being able to look at proportions. Notice that Alban's forehead is much more vertical, and the top of his head is much higher than the Neanderthals. And yet look at the length of the head. The Neanderthal's head is much longer. Alban's is much shorter from front to back. And now look at the face. If you go down from the eyes, you can see that the face of the Neanderthal is quite a bit bigger than Alban's, and yet the chin is really different. Alban has that protruding chin, and the Neanderthal does not actually have a chin. It slants backwards. Let me show you some fossils, the skull and fossils, so you can see those features a little bit more clearly without the soft tissue on top. So here you have, you're looking at the side view of a Neanderthal skull on the top and a human skull on the bottom. So those skulls are on the right-hand side of the screen, and on the left-hand side, we've taken an outline of each of those skulls and superimposed the human on top of the Neanderthal. So the Neanderthal is in red underneath, and the human in orange on top. You can see these same characteristics, that the Neanderthal has that flat forehead, has a longer head compared to the human. The face, it protrudes and it's bigger. And it doesn't actually have a chin. It doesn't have that protruding chin the way that humans do. Let's look at them from the side. So here we have the same skulls, but we have the human on the left and the Neanderthal on the right, viewed from the front. So you can see more of the differences between them. Neanderthals, they have these high, rounded eye orbits. They have a wider nasal opening. The face, it's just a lot bigger. And another thing that's kind of interesting is that Neanderthals had a larger cranial capacity than humans. So on average, the brain of a Neanderthal was bigger than the brain of the average human. We don't know why, although some people have hypothesized that perhaps they were telepathic? I don't know. The humanity of the skeletal form is often portrayed in artistic renderings. So we've seen that there's lots of differences, but there's also a lot of similarities between Neanderthals and humans. And you can see here how the artist for these two pictures really brought out the commonalities with people today, from the styled hair of the woman on the right to the man on the left carrying a small child on his shoulders, gently holding the child's feet for protection, and the child delicately holding on to the man's neck. It's a heartwarming portrait, so similar to one of me and my father when I was a small child, about the same size. But of course, our interpretations of what Neanderthals were like, it tends to say more about what we think of ourselves than about the Neanderthals. The scientists interpreted Neanderthals as hunched over, mean brutes, cavemen, in the early part of the 20th century. But in the 1960s and 1970s, they were reinterpreted to be peace-loving, flower child-type souls. And now, what do you think these portraits, painted in 2017, what do you think they say about us? But before we start getting into that, we haven't finished with the morphological differences between humans and Neanderthals. Let's get back to skeletons. So, I took a picture of this display at the Krapina Neanderthal Museum in Croatia. And forgive me, it's really hard to take a picture of a museum exhibit when it's behind glass, but the point is to show you the differences between Neanderthals and humans. So what you see here is these two figures. One is a Neanderthal, and half of it has flesh on, and the other half is the skeleton. And then you have the same half flesh, half skeleton for a modern human on the right. The red string points to lots of different features on a Neanderthal skeleton, and you can't read them, and I don't want you to. I'm just going to summarize what sort of the main points of when you pull these all together, what they mean. They're telling us that Neanderthals, they had short forearms. They had short legs below the knee relative to humans. They were more barrel-chested. They were short and stocky. On average, males are 5 feet 6 inches tall, or they were, and the females were 5 foot 2 inches tall. In fact, the tallest Neanderthal that has ever been found is only 5 feet 10 inches, which is about average, if even, for men living in the United States today. So one of the things that's really hopefully jumping out at you is that there's a really big difference in the body shapes between Neanderthals and humans. So could these body shapes, this difference, actually tell us something about what was going on, the evolutionary history that led to the Neanderthals? Well, one of the things that's really interesting is that it looks like variation in body shape in hominids, and especially when we're thinking about Neanderthals, follows rules that are applied, that were developed and are applied to mammals more generally. Let me introduce you to those. The first one is Bergmans Rule. It was developed in first proposed in 1847. And in this, it says that for warm-blooded organisms, populations with less massive individuals are often found in warmer climates near the equator, and populations with more mass are found farther from the equator in colder regions. Now, there's another rule, Allen's rule, and this sets that the length of the arms and legs and other appendages also have an effect on the amount of heat lost to the surrounding environment. So populations in warm climates near the equator tend to have longer limbs than do populations living farther away from the equator in colder climates. So there's this interconnection between body temperature, generating body heat, dissipating, radiating body heat, losing body heat, and the latitude at which an animal lives, the species of animal, where it lives. Latitudes, these are those horizontal lines on maps that demarcate how far away from the equator you are in your geography. So let's dissect, let's dive into that relationship between mass and dissipating body heat, losing heat. And this gets us into thinking about surface area to volume. Let's look at two different size cubes. First, this little one. It has 2 units of length along each side. So if you're going to calculate the volume of this cube, you just do 2 times 2 times 2. So the volume is 8 units. Surface area would be 2 times 2 times 6. So the surface area is 24. Now let's look at a cube that's twice that size. So here, the length of each side is 4 units. So the volume here is 4 times 4 times 4 is 64. And the surface area is 96. And then this means that we have a really distinct difference when we look at the ratio between surface area to volume. That surface area to volume ratio is just 1.3 for the small cube, and it's 3 for the larger cube. This means that there's more mass and less surface area when you're thinking about a larger body. So there's some really nice examples of this in the animal world, this phenomena of having the smaller body size with this smaller mass with a greater surface area. And those animals, I've put up an example here for you of a sun bear. So Bergmans Rule is about body size, and so I chose an animal that starts with a B so that it's easy to remember. Sun bears. These are amazing bears that live in tropical rainforests in Southeast Asia. They range in height from about 3.5 to 4.5 feet tall, and they weigh between 60 to 145 pounds. Now, polar bears, they live in the Arctic, and they are quite a bit bigger. The males can be up to 9 feet tall. The females are somewhere between 6 and 7 feet tall. Males can weigh close to 1,000 pounds, and the females somewhere around like 300 or 400 pounds. Hey, do you remember what the term is for that difference between males and females? Yeah, sexual dimorphism. But we see here Bergmans Rule being exemplified by the differences in the body mass. So the smaller body mass with the larger surface area, relatively larger surface area in the animals closer to the equator, and a larger mass and a relatively smaller amount of surface area in the northern latitudes, the higher latitudes, as a way to preserve body heat, to keep body heat, to not lose as much body heat in the colder climates. We see the same thing going on with appendages, and I love to use these hairs for this. So you have the Arctic hare and this desert hare, and what a difference in the size of the ears. A lot of heat would be dissipated from those ears in the desert hare. So we see the same thing excuse me, with Neanderthals, where they have these shorter, stockier bodies, shorter limbs. So we think that they were gradually over time, that they had adapted to these colder climates. I want to take you back to a graph, a figure that you saw earlier. This was from the first module. And here we have temperature, reconstruction of temperature, plotted on the x-axis, and on the y-axis time, going from 65 million years ago up to present day. And we see that temperature has changed over the Cenozoic, and as we get to the end of the Miocene and into the Pliopleistocene at the top of the figure, that you have oscillation in temperature, that it goes up and down and up and down and up and down, and it increases in amplification and also in the frequency of the oscillations. Let's consider this in a little bit more detail by looking at a figure, a chart, that goes from just 500,000 years ago to today. And this graph is plotting global temperatures over the last 500,000 years. So we have time on the x-axis, going from 5,000 years ago to today, and the global mean temperature is plotted on the y-axis. Notice that temperature, it goes up and down as it goes through time. As the line goes up, that means the temperature is warming. As the line goes down, that means the temperature has cooled. And you can see that there are 1, 2, 3, 4, 5 episodes of very cold temperatures. We call these ice ages. And those episodes when the temperature was warmer, we call those the interglacials. This back and forth, this oscillation, this had a dramatic effect on what the world was like, where Neanderthals, where Homo erectus, where hominids, and all these other animals were living. One of the big things, in addition to whether or not it was generally more cold or generally warmer, is what happens to water. During those ice ages, a tremendous amount of water would be trapped in ice sheets, either in the polar caps, the North Pole, the South Pole, and also or in glaciers. And as more water was trapped as ice, that meant that less water was getting into the oceans, and so sea level would drop during the ice ages. In fact, that very last ice age, the last one that we have had, started about 24,000 years ago, ended about 12,000 years ago. During the height of that ice age, sea level was about 120 meters lower than it is today. That's about the equivalent of a 4-story building. That means here in the Bay Area, there not only wasn't a San Francisco Bay, but you could actually have walked all the way out to the Farallon Islands. It was a dramatically different place. Tyranny of the present, right? Always have to keep that in mind. Now, Neanderthals. Remember those earliest Neanderthals, that sort of proper Neanderthals, about 130,000 years ago. Now notice on this graph that is around the time of the ice age that preceded the most recent one. And those Neanderthals existed until close to when the last ice age began. Now think about those bones from Cima de los Huesos at about 400,000 years ago. One of the things that may well have happened is that you had a population living in Europe that was increasingly adapting to these cold ice ages. Let's actually look at a map and think about what was going on in Europe. So on this map of the world, we have plotted where the ice during a glacial maximum would have extended to. And focus your attention onto Europe and notice the Iberian Peninsula, now where Portugal and Spain are. And basically, it's this peninsula out there, and it would have been really difficult for any hominids living in that region to have migrated back and forth from other regions across Eurasia. So Neanderthals were living in those regions below the ice sheets, just south of the ice sheets. And here you can see a map, another map of a reconstruction of where the ice would have been. Now look at that Iberian Peninsula, and you can see a glacier in the Pyrenees Mountains. So more barriers to hominids being able to travel back and forth. If you look at the extent of where the Neanderthal sites have been found, we can see that they do seem to have been influenced by where ice would have been located. And they go far out into Asia. I've added some extra sites on here for you. Now, we want to understand a little bit better what happened to those Neanderthals and how they interacted with Homo sapiens. How do they interrelate with Homo erectus? What was going on with all of that? So for this, you need to wrap up this part of the video, go do your activity, and I'll see you in the next video.